Okay, we will continue our discussion on noise and angle modulation. I think we have now a reasonable idea of the fact that angle modulation indeed is a good thing to do in as far as performance of the modulation scheme in the presence of noise is concerned, right. We find that there is a nice trade-off that is available to us for getting improved performance at the cost of increased bandwidth, right. That is of course there. Now if you just recollect, we have derived the expression for both the case of FM as well as phase modulation, right. And when I say angle modulation, it refers to both, it refers to any one of them or any variant of them, right. Now if you look at, if you specialize these expressions for the case of tone modulation, that is your modulating message signal is a pure sinusoid, right. You can reduce these expressions. I will leave that as an exercise for you to do. It's very simple exercise to the following expressions. So for tone modulation, you can check that the expressions for the output SNR reduced to these very simple expressions: 3/2 beta square gamma for the case of FM and half beta square gamma for the case of phase modulation, where beta of course is your modulation index defined as peak frequency deviation, ratio of peak frequency deviation to the highest, to the frequency of the sinusoid, modulating sinusoid, delta f by FM. Remember, beta is delta f by FM, and these expressions come basically by understanding what is the nature of these values. Remember, this was a factor that appears in the expression for the FM case, and the expression that appears for the PM case is m square bar upon np prime square, right. So basically by evaluating these two expressions for the case of tone modulation, right, you get this result. So I am leaving that detail as an exercise. It's very, for example, it's very obvious that m square bar upon np square for the case of a sinusoidal signal will be equal to half. So use that fact and you will get this expression, right, and use the definition of beta and you will get this expression. Now the reason why I wanted to write these expressions is because that allows me to draw a set of very simple curves for output SNR against gamma. So of course, before I go to that, please note that for tone modulation signals, which one is superior? FM is superior, right. In general, we have discussed under what situations FM will be superior and PM will be superior, right. That was a separate thing that we discussed, but specifically for the case of tone modulation, FM is superior by a factor of 3. That means it produces 3 times output SNR that is produced by a PM for the same value of gamma. 3 times means 4 dB, so it is superior by 4 dB, 4 decibels, right. So that is one fact. The second is the interesting relationship between gamma and output SNR. It is of course just like the case of AM, it is a straight line, but it's a straight line with a slope of beta square, right. So of course that's, if I were to plot it on a log scale, which is a usual case, so if I plot it in decibels, this also being a log scale in decibels, then how will the dependence on beta square will come out? For different values of beta square, suppose you take beta square as a parameter, then essentially it will be log of beta square plus log of gamma, right. So for different value of beta square, you will essentially get different straight lines, right. You get a family of straight lines which are parallel to each other, right. So this is what you will get, a family of straight lines. Okay. So for example, this could be for beta equal to 2, for beta equal to 4, for beta equal to 6, etc. Right? And as you know, for every doubling of the let's make it 8 here. For every doubling of beta, which means doubling of bandwidth, the output SNR will improve by 6 dB. So this gap is how much? 6 dB. Right? As you go from beta equal to 2 to beta equal to 4, the curve goes up by 6 dB. Right? Similarly, when you go from 4 to 8, the curve again goes up by 6 dB. Right? So that's something that you must know. But you will also have noticed a curious thing that I have done here. I have not taken the straight lines like that, right? And I think you can guess why. Because we discussed this analysis has been carried out only for the small noise case. That is, when the signal to noise ratio of the input, the value of gamma, the input signal to noise ratio in the message bandwidth is sufficiently large, right? The moment you make it smaller and smaller, the analysis becomes invalid. So these results that we have plotted would no longer, we simply can't say the straight line behavior will continue on this side, right? Actually, the straight line behavior ends somewhere here, like this. Okay, and you get a very different situation in that as the noise increases or the input signal power decreases. Right? So let's look at that issue now, and that's the same issue which I discussed in the case of AM earlier, namely the threshold effect. Right? That is, as the input signal to noise ratio decreases, unlike these straight line curves which imply a corresponding graceful degradation also of the output SNR, beyond a certain point the output SNR will decrease much more than the reduction in the input SNR. Right? Then that is dictated by the reduction in the input SNR, and that kind of effect will occur much more pronounced now than it was for the case of envelope detector in the case of AM. Right? So the threshold effect phenomenon is a very important phenomenon in the context of angular modulation. It is not so important in the context of amplitude modulation. If you remember, I discussed this issue earlier. For the case of amplitude modulation, it is hardly relevant. Right? Theoretically, it is there, but practically it is of hardly any significance. But for the case of FM, it is of great significance, angular modulation. So we look at that issue and look at the threshold effect in angular modulation now. Okay. Unfortunately, the analysis of this case is much more difficult, and we will not be able to do the proper mathematical analysis because that's quite involved and beyond the scope of this course. There is a case where the noise power is either less it should be the other way around. Noise power is either greater than or of the order of the signal power or carrier power, right? Then you are in the threshold region, that is the performance degrades. So this is when the threshold effect occurs. So all of you understand what I mean by the threshold effect. That is, the output SNR performance becomes suddenly very poor. It doesn't go along the straight line anymore. Okay, it goes much worse than that. We want to understand. So since the analysis is going to be much more difficult in this case, we'll just try to qualitatively understand the phenomenon. Right? I think that's where most of the effort will lie. So the second important point I want to make in this connection, which I already said, that it is much more pronounced. This threshold effect is much more pronounced in FM or PM than in AM. And remember, in AM it does not occur always. It occurs only when you do envelope detection. invariably threshold effect is a phenomenon arising from the nonlinearity in the system, right. As long as you are doing synchronous demodulation, your entire system, modulation and demodulation system, was a linear system. The combined system was a linear system, right. The moment you put an envelope detector, it became a nonlinear system, right. In the case of angular modulation, modulation itself is nonlinear, right. So the system is nonlinear, right, and therefore the threshold effect will occur. So let's look at some kind of a qualitative discussion as to what is this threshold effect, why it occurs, and what it does to the performance, right. So basically that's what we will limit ourselves to. I'll just give you a feel for the threshold effect. To do that, let's return to the phasor diagram that we had been studying earlier. This was your carrier amplitude A. For simplicity, I will call this angle psi, right. Remember, this was psi of t. This is your noise phasor, right, and this is your resultant phasor. Remember this? I am not calling it omega ct plus psi, because you can assume that the whole reference is rotating at a rate of omega ct. Reference plane is rotating at that rate. Now notice that ENT is a fast fluctuating phasor, right, and this phasor, the carrier phasor, is this angle psi is a slow fluctuating phasor, because fluctuation in the phase of the carrier phasor will be dictated by the behavior of psi of t, and psi of t is kp times mt, right. So the rate of variation of psi is much slower than the rate of variation of angle and amplitude of En, because the bandwidth of ENT is, remember we have used this argument earlier, it is not a new argument, right. So bandwidth of this is much more than the bandwidth of psi, which is the bandwidth of the message signal mt itself. This is b and this is twice delta f plus b, or delta f plus b at the baseband level, right. So this fluctuates much more rapidly. So that is why we could make the assumption last time that psi is nearly constant while this is fluctuating, and we did the short term analysis. That was the basis for the results that we obtained. So basically what we are saying is that as psi remains fixed for quite some time, ENT keeps on rotating, keeps on fluctuating both in amplitude as well as in angle. But as long as the amplitude of ENT is small, as a result of this rotation of ENT, or amplitude variation and rotation of ENT around this phasor, there will be minor variations in delta psi, right. Delta psi will keep going up and down around this mean phasor. Is that okay? As this carrier phasor keeps rotating, while psi is fixed for quite some time, the resultant of this R will keep on fluctuating in angle around the mean angle psi. Is that okay? That is a physical picture, as long as ENT is small. Now the important thing to study now is what happens when ENT becomes large, right. When you say ENT becomes large, you are not saying it is large all the time. What we are saying is that there is sufficient probability, that there is a finite significant probability that suddenly ENT becomes very large and remains large for some time, right. Typically if a signal has some bandwidth b, let us say if the signal has some bandwidth w, right, then it can stay on any particular amplitude, in the neighborhood of any particular amplitude, for a time period which is of approximately of the order of 1 by w. This is just a manner of saying that its time constant is 1 by w. It changes its values at the rate of 1 by w, right. If you can think of this as being the highest frequency component present in the signal, right, and therefore generally the rate of variation of amplitudes will occur governed by this highest frequency, or it cannot be faster than this, right. So roughly you can say this is just an intuitive discussion that the signal stays at a particular amplitude level or in the neighborhood of a particular amplitude level for a time which is proportional to the reciprocal of the bandwidth, right. Just take that as a intuitive picture or intuitive meaning of bandwidth, right? So we'll just keep that in mind. So basically what we are saying is, when there is a finite probability that ENT suddenly becomes greater than A with some significant probability, that is, the probability of this event becomes significantly large. When ENT is much less than A, when signal power is much larger than the noise power, the probability of this event happening is going to be negligible. The threshold effect occurs when the probability of this event becomes significant, right? Now what can happen? So what we are saying is, for some time duration, this happens. This is not true for all the time, but this happens for some time duration, typically of the order of 1 by W, where W here is delta F plus B, right? There is a noise spike, and there is a probability of a noise spike occurring becomes significant, right? Noise spike of duration 1 by W, where W is delta F plus B here. Okay, such a noise spike can occur in any case, right? Can occur even when the noise is small, but the probability of this occurrence is going to be very, very small. So we are not concerned about that. But the probability of such a noise spike occurring becomes large when your carrier power is much less than the noise power. So a few statements that I made here are very significant. First, this event has a significant probability, and this event essentially means occurrence of a large noise spike. Right? And the duration of this spike, whenever it occurs, is going to be of the order of 1 by W. These are the 2 or 3 statements I made. Right? So what happens during this duration? What happens to this phasor diagram in this duration when such a large noise spike occurs? That's what we need to understand. Right? When it is small, we know that delta psi rotates like this. It's basically delta psi is going to vary around psi with the mean value. Right? When ENT becomes very large, the kind of situations that you can have, let me draw a separate picture. Let's consider this noise spike occurs, this duration is of, this is your 1 by W. Let me consider 2 or 3 instants within this spike. Let's say T1, T2, T3, etc. Where this amplitude is significantly large. So during this interval T1, T2, T3, the amplitude of noise is significantly large compared to A, much larger, right? So what happens to the phasor diagram? Let us say you have, this is your reference phasor. At time T1, your carrier phasor was here, and suddenly you have a very large noise spike at time T1, right? So this is ENT1. This carrier phasor remains of the same amplitude because this is psi, right? And within this noise spike duration, you have another value which is, we are just talking about this ENT is fluctuating very fast, right? So it suddenly goes to, let's say, another value like this. It's rotating around this, remember, and both its angle is changing fast as well as amplitude is fluctuating, right? But during this entire duration, the amplitude is large. That is what we are saying, and the angle is fluctuating. These may not be equal, but they are both very large, right? So what is the value of, so in this case the resultant phasor was here. What is the new resultant phasor? The new resultant phasor is here, right? And it can happen that your T3, at time T3, you may have, for the same carrier amplitude, let's say your this phasor goes like that, right? It's fluctuating around A, right? What is the new resultant phasor? So now do you see what is happening to delta psi? Look at what is happening to delta psi. This is the value of psi. The value of delta psi is this much here, right? At time t1, it is this much here, and it almost becomes 2 pi at this point. So the phasor, the noise phasor within that spike duration is going from this position to this position. I have just captured 3 positions, right? One can trace the whole path, right? I have just captured 3 positions. At time t1 it was here, time t2 it was here, and time t3 it is here. There is almost a rotation of the delta psi goes through the rotation of nearly 2 pi radians. Right? So instead of a small value of delta psi around the mean value of the actual value of a phase, what you are now finding is that the phase error suddenly becomes during the occurrence of this noise spike very large. Right? Now what is the effect of this? So what you have is a very large phase spike, right? So if I were to plot this as a function of, if you look at the output of your FM phase demodulator, which will be proportional to psi, or psi plus delta psi. Psi is constant, so I am not worried about that, right? Let us look at delta psi as a function of time. Look at delta psi as a function of time. So what is happening is, most of the time the noise is small and delta psi is fluctuating around some mean value of psi, right? Suddenly this spike occurs and there is almost a phase rotation by 2 pi radians. Either 2 pi, see 2 pi is a manner of saying, it could be 2 pi, it could be some other large value. That is not very important. So what happens? Suddenly your phase error jumps by this amount, right? In a time interval which is of the order of 1 by w.
Because of the magnitude.
Sorry?
Because of the magnitude.
Because of the magnitude, because of large, because suddenly this becomes very large, amplitude becomes very large, and you go through this phenomenon during this time. So the output of the phase demodulator will show up like this. You are getting some constant value of psi with some fluctuations, and suddenly there is a jump. Then as long as you are here, it will be like this, right? And once again, after some time, whenever the second spike occurs, there is another jump. So this will be the behavior of the output of the phase demodulator now. Instead of continuing to remain like this all the time, this indicating noise and this remaining the constant value of psi, you will go through these jumps, right? The time interval here of this duration is going to be of the order of 1 by w.
So are we plotting the value by like modulo 2 pi?
No, this is not modulo 2 pi. Modulo 2 pi values will be the same, right? Modulo 2 pi values will, but then the fact that it is 2 pi is incidental. It could be some other value, right? Some other large value. Okay.
So 1 by w is the time for which the first.
For 1 by w is the time for which each spike duration lasts. It's a typical average duration of a spike.
So then it will also come down.
Yeah, so this was the beginning of the spike, this is the end of the spike, during which time this phase rotation occurred. I am plotting delta psi t as a function of t. Right? After that it starts behaving in the same old way. Right? After that it starts behaving in the same old way. Is it clear? Right.
Delta psi can be only as large as 2 pi, it can't be more than 2 pi.
Typically well, theoretically it can be anything because it depends on the kind of fluctuation that this goes through, but yes, 2 pi will be a typical value. I agree with that. Now what happens to this is the phase demodulator output. What happens to the amplitude demodulator output? FM demodulator output. FM demodulator after all is obtained by passing the output of the phase demodulator by through a differentiator, So the behavior that you will see will be more or less the same, except that it will be differentiated version of this, right? So you will see some fluctuations, and corresponding to this you will get a pulse, different derivative of this, right? Step function. Similarly, so you will see something like that. Okay, so this is delta psi dot t, the derivative of this. This is what it will look like. So FM demodulator output will look like this, phase demodulator output will look like this, right? And now how does it make a difference to the noise power output? Remember, no matter whether we are having the small noise case or the large noise case, the demodulator is followed by a low pass filter of bandwidth B corresponding to the message bandwidth, right? And our argument earlier was that most of the noise power outside this bandwidth will be removed by this filter, right? So how does that picture change when your behavior of noise is like this? The picture changes in the following way. Although that picture is still valid, but the fact is that these sudden jumps in the output, or these pulses in the case of FM, they have significant amount of low frequency energy. If you look at the spectrum of these, the spectrum of the unit step function or the spectrum of this pulse, right? Most of the spectrum is concentrated at low frequencies. So there is a significant energy of these pulses or these jumps which lies within the bandwidth of your message signal, and you will not be able to eliminate that, right? And this suddenly increases, right, because of the increased occurrence of these pulses. As long as the noise amplitude is small compared to the average signal power, average carrier power, the occurrence of these pulses is very, very infrequent, right? So it doesn't matter. But the moment the reverse happens, these pulses occur with much more frequency, and suddenly there is a large amount of energy which lies within the large amount of noise energy which lies in the bandwidth of the message signal, which you cannot eliminate with that final filter that you have, baseband filter that you have, and suddenly the noise output power becomes much larger than otherwise. So that's the reason that suddenly your output noise power increases and the threshold effect occurs. Performance degrades significantly. Are you with me on this? This is an intuitive picture. This is a qualitative picture. This is what leads to. So let me write down some of these points that I just mentioned for completeness. So when, based on this discussion, we can say that when this event occurs, right, psi t has significant jumps, and delta psi dot t, delta psi t, not psi t, and delta psi dot t has spikes, almost like impulses, right, with significant frequency or significant probability of occurrence. That is, they keep on occurring frequently. This kind of situation keeps on occurring frequently, right? And this in turn, we note that these kind of jumps and these kind of spikes, they have considerable power or energy at lower frequencies. And this leads to increased noise power at the output of the final bandpass final baseband filter. And that is the reason for disproportionate increase in the output noise power as compared to what you should have expected because of the decreased SNR in the input, right? And that's why you have a threshold effect. So your analysis earlier did not take into account these spikes, because these spikes did not occur or occur with very, very low frequency, very, very low probability. But this new analysis will have to take this into account, this analysis which is for the case of high noise case. Okay, so this leads to the threshold effect. Okay, so there is a more precise mathematical analysis that one can do, and one can work out a precise expression for the output SNR in the threshold region. But since I have not gone through the mathematics of it, the expression I like you to look at in the book itself. There is no point just writing the expression here. But let me draw the picture for you in terms of the SNR curves. So if you look at the SNR curve at the output in terms of gamma, right? I'll use the baseband case as a benchmark. Remember, in the baseband case, output SNR is equal to gamma, right? Always this has been our benchmark, right? And what we learned that for angle modulation, as you increase the modulation index, right, your output SNR increases, right? Now, taking into account this threshold effect, the actual curves, they, instead of going like that, they go something like that. That's the threshold effect. So at this point, simply you start deviating from the straight line curve very significantly, right? And as you increase the value of beta, it's very interesting. I'm not proving all this. As you increase the value of beta, this threshold becomes more and more significant, right? This will occur much earlier than it occurred in the case of smaller bandwidth signal. So this can occur instead of going like this, instead of going like this, so it will go like that now. So you notice two effects. That there is a threshold effect. That is the first point. The second point is the point of occurrence of the threshold. That is the value of gamma at which the threshold becomes threshold occurs is larger for the larger values of bandwidth than for smaller values of bandwidth. Is it okay? So the point of occurrence of threshold is not same for all values of beta. It is different for different values of beta. In fact, one can prove that the point of threshold using the same kind of arguments that we use for the case of AM, but much more involved, is approximately equal to 20 times beta plus 2. So the larger the value of beta, the larger the value of gamma at which the threshold occurs, right? And what would you like? You would like the threshold to lie on this side or on this side? On the lower values of gamma, right? So unfortunately that doesn't happen as you increase the value of beta. So threshold becomes more and more significant as you go for a higher and higher value of beta in order to get better performance. So there is a kind of contradiction here. If you go for larger values of beta, you get better output SNR provided you stay above the threshold value. Input SNR stays above the threshold value. But at the same time, you are buying the probability that unless you are significantly above the threshold value, you can come into threshold region and suddenly you get a very large noise at the output. If you ever listen to a FM radio carefully, particularly sometimes when the signal conditions are not so good, right? I don't know whether that typically does not happen in a metro-like situation where the power is significantly large. But if it were to happen, what you will see is suddenly when that situation occurs, a crackling sound, a very large crackling sound, and that is because of the large noise. And that crackling sound is basically due to those noise spikes. And this in FM literature is known by the name of clicks. You call this noise as a click noise. This crackling noise is called click noise, right? Of course, I already explained how that click noise occurs. So it is heard in the form of crackling sounds. So we have to therefore keep in mind that while FM in general is much superior to AM above threshold, we must keep in mind that it can become very bad below the threshold region, right? So you have to keep the input SNR at a significantly good level so that you are above the threshold region. Okay. Now in this context, let me passingly mention, again it is outside the scope of our discussion here, when we discuss FM demodulators, remember we discussed various kinds of demodulators, namely the simple slope detector, right? And then we discussed PLL, then we discussed frequency compressive feedback, right? At that stage, let's look at the discussion I had on frequency compressive feedback. I don't know how many of you remember what we do there. What is the effect that we create there? In the frequency compressive feedback system, if you recollect, there is a discriminator right inside the feedback loop, right? And you remember we discussed why should we go for that kind of a system if you are going to ultimately have a discriminator. You can have a discriminator even without the feedback loop, right? But then we learned that if you do that, the kind of FM signal which is going into that feedback loop, into the discriminator, is going to have a much smaller value of beta, remember that, as compared to the beta that you have at the input, right? And now you see why that is important, right? That you may have a large value of beta because you want to work with a large bandwidth. At the same time, you don't want a large value of the SNR threshold SNR, right? So you try to effectively reduce your value of beta for the purpose of demodulation, right? And frequency compressive feedback is a mechanism by which you can do it, and that is why it works. It's a preferred system when threshold effect is important to worry about. Similarly, the phase lock loop has a much better performance as compared to the simple discriminator in terms of threshold performance. Okay, so I'll just close this discussion here, connecting this up with what we discussed earlier, right? So think about it. If you have some questions, we can discuss it. Okay, now we have a little limited time now, so I have to optimize my time, and to do that, one topic which I intended to discuss in detail, I will discuss only very cursorily now, but I will request that all of you try to read it up on your own for detail, and that is, I would like to return to the subject of pre-emphasis and de-emphasis. Remember we discussed this subject in some other context earlier. Okay, as I am saying annual modulation systems, this is what I will not be able to do. I will very briefly discuss the concept of pre-emphasis and de-emphasis in the context of noise for general baseband systems first, very briefly that also, right, and then ask you to read how these concepts can be extended to the case of annual modulation. When we discuss the case of interference, narrowband interference, we have already discussed this issue, right? But I want to now generalize the discussion to the case of noise and show that in general the concept of pre-emphasis filtering and de-emphasis filtering helps us to improve the performance of systems, all kinds of systems in the presence of noise, but particularly so in the case of annular modulation systems, right. So basically if you recollect the model, let's look at the baseband system. In the baseband system, you have your message signal coming in, which has a power spectrum of Sn omega. Before you transmit it, you pass it through some filtering. You do some filtering of this. This filtering basically will modify the spectrum of the signal. Therefore, in that sense it will distort the signal also. But you want to do this filtering sometimes to take into account certain facts that we know about the communication system. For example, the communication system may be better suited to work with, let's say, either higher frequencies or lower frequencies of the message signal, right? So suppose it performs poorly for higher frequencies, then what would you like to do? You like to suppress the higher frequencies. If it performs you like to enhance the higher frequencies because you like to increase the SNR of the higher frequencies, right? So the pre-emphasis filter will be able to do that. But in the process, you're going to distort your signal, right? So what you will do is you have to carry out the corresponding compensatory filtering at the receiver, right, which is called the de-emphasis filter. So the complete communication system will, at the transmitter, have a pre-emphasis filter, at the receiver have a corresponding de-emphasis filter, so that the combined product of these two is constant, right? To keep the discussion more general, you may also have a channel with some transfer function Hc omega, and of course you have noise, which is the additional complication that you have now. That's the complete picture. Finally, you want, as far as the message is concerned, if it has a certain power spectrum shape at the input to the system, you must have the same power spectrum shape at the output of the system, so that the message signal remains undistorted, right? In the process, the performance, SNR performance of the output can be improved if you choose your pre-emphasis and de-emphasis filters appropriately. And I want to discuss very briefly what kind of optimization you can do in the choice of these filters to improve the output SNR. I am not really doing this discussion in the context of angular modulation, which is what I have written here, right? I will do this in the context of baseband systems, but the ideas can be extended to very simply to the case of angular modulation. This is a baseband system model. So what is the problem? Problem is to determine the best choice of HP and HD. With what objective? How do you define best? Best in our case would be to maximize the output SNR, right? That's the problem. We did not consider this issue so far because we assumed our filter was, this HP omega was simply removing so far the outer band frequencies, right? Both HP and HD omega, we were simply removing outer band frequencies. But now we are allowing them to modify the spectrum also, keeping the overall constraint that these two should be the same, right? So if you were to do that, we know that for distortionless transmission we must meet certain conditions. And what are the conditions? That the magnitude of the product of these three transfer functions, HP omega into the channel transfer function into HD omega, should be equal to a constant over the frequency band of interest, right? Let's call this G. Also, the corresponding phases, phase function of HP omega, let's call it theta p omega. The phase function of HC omega, let's call it, the phase functions will add, isn't it? When you put three filters in cascade, the phase functions will add. The actual transfer functions will get multiplied, and since the phase function will occur in the exponent of the complex function, the exponents will get added, right? So theta p omega, theta sub c omega plus theta sub d omega, it should be equal to a straight line, right? Minus omega naught into t sub d, or omega c into, sorry, omega times t sub d, as a function of omega it should be a straight line, right. Linear phase characteristics or constant delay characteristics, right. So if you were to formulate the problem mathematically, this is what we want to do: maximize output SNR, S naught by N naught, for a given transmitted signal power, for a given S sub t, right. S sub t is your transmitted signal power or received signal power. Can you express S sub t in terms of Sm omega? Sm omega is the power spectrum of the message signal. It will be the area under the power spectrum of the message signal. So S sub t, sorry, not the transmitted signal is not this. This is the transmitted signal. You are modifying the spectrum of the message through the pre-emphasis filter. So the power spectrum of the signal here, the area under that would be the transmitted power, right. So S sub t is Sn omega into mod hp omega square d omega. The area under that is the total message power that is being put on the channel, right. Let's assume that the channel does not attenuate, right. In any case, attenuation factor can be taken into account separately in fixing the ST value. What can you say about, so your problem is to maximize your output signal to noise ratio for a given value of ST, which can be written like this, right, which depends on HP. Okay. So now to do this, you must write the expression for output power, signal power, output noise power, take the ratio and maximize. That's what you need to do. What is output signal power? Output signal power, final output is what? Sm omega. So output signal power is simply, sorry, I made a statement that we are assuming that let there be no attenuation. Sorry, that's not correct. Attenuation is contained in this factor of G, right? Attenuation or gain or whatever you like to call it. So output SNR, output signal power would be G square times, tell me, integral of Sm omega, right. This is the final signal you are getting, this is the attenuation factor, this is what you are getting. What is the expression for output noise power? Let's say the noise has we are considering the general case, you could consider white noise, but let's consider a general noise which has some power spectrum Sn omega. When you consider white noise, you can always put Sn omega is equal to N naught by 2, right. So Sn omega times, tell me, can you speak out? Hd omega, because noise will only go through this transfer function, the receiver transfer function, d omega, right. So therefore the expression for S naught by N naught is G square integral of Sm omega upon integral of S sub n omega into Hd omega mod square. So now our problem becomes the following. This is the expression for the output SNR. You want to maximize this. Let me call this equation 1. So with a constraint. And what is the constraint? Because one trivial way of maximizing this would be to maximize the transmit power. Keep on increasing your Sm omega. Keep on amplifying your signal. Right? So it will keep on getting maximized. But that will give you a trivial solution. Then the answer would be make signal power infinity. Right? So that's a trivial solution. But obviously there is a limit to the amount of signal power that you can transmit for various reasons, right. For various practical reasons you will have to, so there is a constraint with which you have to maximize this, right. So basically you want to depend only on filtering to do your optimization, to increase your output SNR, not the brute force solution of increasing the transmit power, right. So maximize one with the constraint that S sub t should be equal to some fixed constant. Okay. This is a problem. I do not know whether you solved this kind of problems in mathematics earlier. You have done constraint optimization problems, right? In any case, we will not use any of the mathematical formal tools to solve this problem, because the proper tools that are required is the calculus of variations, which I am sure you are not. I do not know whether you have done it or not, but we don't require it, fortunately. Fortunately, there is a very simple result in mathematics which helps us to do this optimization almost in a trivial manner, right. But since the time is up, we will stop here and very quickly do the discussion next time, and then move on to pulse modulation schemes. This is the next topic.